Okay, so next we are going to find part B, the work done by the object's weight force. So we know that the weight force work done can be written using the work definition. W is the force, D is the displacement. And once again, this becomes WD cosine of another angle. It doesn't, this theta, I'm keep writing theta, but it doesn't mean it's the same one. We just need to check. And going back and looking at my free body diagram, now I'm thinking about the orientation between D vector and W vector. And as you can see on the free body diagram, they're opposite to each other. So what is that angle then? It should be 180, right? So this is one way of finding work. So let's find this first, and then there's another way that we can find the work done by the weight force, and I'll discuss that. W is mg, and times D times cosine 180. So M is given as 75 kilograms. G is 9.81 meters per second square. And D is 10 meters. What is cosine 180? It is minus 1. So as you can see, we're getting a negative value. That makes sense because force, the weight force, and the displacement are opposite to each other. So the work done should be negative. And the number we get from this is less than the work done by the tension force, and it is 7,358 newtons meters. Means it's joules. You can write this in kind of, if you like, 3 sig figs, and that would be negative 7.36 kilojoules, right? So that's the answer. Once again, this is in magnitude, this is less than the work done by tension. What other ways that we can use to figure out the work done by weight force? If you read the material, you should know that the work done by the weight force is associated with the change in potential energy. So when you apply energy conservation, you either use the work done by the weight force on the right side in the work term, or you gotta ignore it and then use delta U, the change in potential energy, because potential energy is related to elevation change, and the weight force does work if there's a change in elevation. So they mean the same thing, but they will have different signs because it's either you're putting on the left side or the right side of the equation. So what I'm trying to say is delta U is negative work done by the weight force. Okay. Instead of saying that, so I'm supposed to get delta U as positive 7.36 kilojoules. Let's find out what delta U is. Okay. And then using that definition, if I've not done this calculations that I'm showing right now, I could have just used delta U instead. And I'm kind of proving that they should give you the same thing. What does delta means? It is final minus initial, right? That's the difference. And what is U? It is the potential energy in the form of mgy final minus mgy initial. So let's write this down. We have mg, right? And I'm gonna take a parentheses, common parentheses of mg, and I'm writing it this way. And that should give us, m is once again 75 kilogram. G is 9.81 meters per second square. What is final y? Since we said the origin is at the bottom, the initial y is going to be 0. Final is going to be 10 meters, right? So 10 meters is y final. Initial is 0 meters. And what do you get out of this? The same thing, of course. And that should be positive in this case. 7,358 joules, or 7.36 kilojoules, right? And again, this is delta U, and since delta U is negative of work done by the weight force, then you can say, okay, work done by the weight force is negative delta U. If delta U is 7.36 kilojoules, work done by the weight force should be negative of that. And you can see that they are the same thing as they should be. Okay, so this is another way of doing it. And in the energy conservation equations, we'll see how to use. We have to choose which one do we want to use. Do we want to keep delta U, or do we want to keep work done by the weight force? Not both of them. That would mean double counting, and we don't want to do that. Okay, so I'm gonna end it here again, and I'm gonna work on the next step in another video.